So before I go any further, and I think Oliver, I might need a bit of help with you with reading chat with this, I'd just like to try and get a sense of what people already know, so I don't try and teach grandmothers to suck eggs. So if you could just drop in chat whether you're familiar with terms like a circular economy or a linear economy, whether that butterfly diagram that's up on the screen now, whether that's familiar to you or not.
No messages in there yet, so
okay.
maybe worth starting from the start.
Yeah, I will take the silence as let's have some definitions. So this is the Ellen MacArthur Foundation's butterfly diagram. So the idea of a linear economy, which is broadly the one we're in at the moment, is you extract some natural resources. That would be up at the top here with mining or materials manufacturing. They would go through some manufacturing processes before eventually reaching a consumer who uses it and at the end of its life disposes of it, and it goes somewhere like energy recovery or landfill. It doesn't get retained, it doesn't get turned back into anything else, it's just waste now. But the wings of the butterfly are the circular economy. And the idea there is that instead of simply extracting natural resources, processing them, and then throwing them away, we retain them within the economy for as long as possible. So at the end of life, there is some form of recycling, reuse, and you end up with a material that can go back into the system at some point, perhaps as effectively raw feedstock again, but more likely as some other part of this great big ecosystem of materials and products. It's quite a complicated system. We're in the linear one, we're trying to build the circular one. What I'd like to do over the course of this talk is to take a device as an example and just sort of walk through some of the options that we have post-user, basically post-consumer. I am from a medical device background, so it is going to be a medical device I use as an example, but I hope that over the course of the talk you'll see that actually I'm just using it because it gives us a range of materials to play with. And the other thing I'm going to do with it is I'm going to completely ignore every step in the manufacture process, and we're going to start thinking about it here, where the consumer or the user throws it away. And we're just going to have a look at some of the options we have there. So we're going to start with the first one, which is the big bad. It's landfill. Nobody likes landfill. It has a terrible rep. That is mostly deserved. I hope I can bring some nuance to that conversation, but nobody likes landfill. About 44% of our annual plastic waste in Europe is landfilled. And at this point, I'm hoping to bring in some nuance because actually for plastic waste, landfill isn't a completely terrible option. Most materials that are stable, almost all of their carbon emissions across their life cycle, they're before this stage. They don't happen in landfill. Stable plastics in a well-managed landfill, that is one that's up to European or modern American standards, doesn't degrade into greenhouse gases. It's a pretty good carbon sink. You do get environmental damage if the waste materials get out of the landfill, though. You can have leachates, you can have things becoming microplastics or becoming plastic waste in the environment. And the other flaw with landfill, of course, is we've just spent a huge amount of energy making this piece of plastic, making this piece of metal, making this product, and now we've buried it in the ground and we're not continuing to use it. So now we have to go back to the natural resources and keep extracting, and that's not a sustainable approach. That's plastics in landfill. If you have degradable or compostable materials in landfill, it's a bit of a different issue, and it is actually quite a bad problem. The reason it's a problem is you get methane reduced through anaerobic decay. So if something's capable of rotting, it's going to rot. If it doesn't have enough oxygen, it's going to rot and release methane instead of CO2. CO2 is harmful enough. Methane is about 80 times as bad in terms of global warming potential. Over 20 years, a kilo of methane will have the same effect as 80 kilos of CO2 in the atmosphere. So food waste in landfill per 1,000 kilos, you're releasing about 300 cubic meters of methane. And the reason that municipal solid waste releases methane is because you have biodegradable, compostable materials within it. You can manage this. A lot of modern landfills collect the gas. They either collect it and sell it on, or they collect it and flare it. While that's not ideal, burning the methane into CO2 does reduce the immediate impact. As of about 10 years ago, half of the landfill gas in US landfills was being collected and either flared or used like this, which kind of implies that half of it wasn't. I'm not sure how much that's improved over the last few years, but you can see why getting biodegradable things into landfill is going to cause a problem. It's these biodegradable things that lead to this maximum emissions of about 1.3 kilos of CO2 equivalent per kilo of waste in landfill. So you can mitigate those depending on how you manage your waste stream, but there is serious emissions associated with landfilling. So I'm not going to suggest you design towards landfill, or that people should design towards landfill, or when you're throwing a product away in your own homes, you should be aiming for landfill. I will ask that you don't immediately dismiss it as an option. Considering our device that we're using as an example, the cardboard absolutely shouldn't go towards landfill. That's going to rot. That's probably going to rot into methane. The plastic casing, on the other hand, given that it's unlikely to be made out of an easily recycled material and it's clearly got colorants in it, if we can't reasonably recycle it, landfill may be the least worst option. So in terms of design, and this is going to be a bit of a theme, this idea of being able to separate things out and send each thing where it's served best. So cardboard, keep it out of landfill. Plastics, if we can't do anything else, at least it's secure and not going into the atmosphere. So it leads us to design questions like, which bits of this device end up hazardous? Which bits of this device need to have additives? Which bits of this device can rot? So that's landfill. It can sort us out with stable plastics. It's not brilliant. It's not as bad as incineration, which is what I'll talk about next. The Ellen MacArthur diagram is talking about this as energy recovery. I'm going to speak more broadly on incineration. Energy recovery is specifically using waste as fuel. Incineration more generally doesn't always do that. So the logistics for incineration are pleasingly straightforward. You collect all of your waste into a mixed stream. Valuable components such as metals or easily recycled plastics or glass, they tend to be retrieved. And you then use fuel to burn the waste. The other very useful thing that incinerators do is they often make dangerous waste safe. So, for example, most hospitals have an incinerator on site, and that's because once something's become hazardous due to contact with, say, an infectious patient or contact with blood products, you really don't want to be handling that like ordinary waste. For the sake of keeping everybody safe, incineration is quite a useful tool. About 40% of our plastic waste is incinerated. That's pretty typical with Europe. The US landfills a bit more than we do. And it does have a couple of advantages. It doesn't release methane because it burns stuff straight to CO2. You don't get plastic getting into the environment so much, and dangerous waste can be handled this way instead of having to store it up. However, you are producing CO2, you're releasing it directly into the atmosphere. We're still taking objects that we've put energy into and setting them on fire. You can make an argument that if you're using waste as fuel, then you're removing the use of fossil fuels. You're replacing other fossil fuels. Personally, I don't put much weight behind that argument. I think we should have a fully renewable energy grid, and I hope that we'll get there within my lifetime. So I'm not happy to say that this approach is removing fossil fuels from the equation. And the estimates in terms of kilograms of CO2 equivalent for this way of sorting waste vary from 0.7 to 1.2 kilos. So we're sort of comparable with the worst end of landfill here. It is sometimes a necessary evil in terms of things like hazardous waste. That's coming from a very medical standpoint. Most of the time, incineration is not the only option. And again, I'm not going to suggest designing towards incineration, but it is something to be aware of when you're thinking about how you're managing waste or end of life for a product. So in our case, with our example device, we could incinerate every part of it. And if the only bin in the room when it's opened is the medical waste bin, every part of it will get incinerated. Because once stuff goes into a hazardous waste stream, it generally is not retrieved. So when we're designing for that, we can ask questions like, does the entire cardboard packaging have to come off immediately before use, or can we make sure that the user's next to a different bin at that point? In terms of, can we redirect any parts of the material or any parts of the device to a different waste stream? The same questions are starting to come up again. Can we separate it into single materials? Can we separate out the valuable stuff? can we keep the hazardous things, so in this case blood contact, away from the rest of the components? All of these things make it more likely that we can retrieve some value and some energy from this before it all ends up going into the incinerator. That's incineration. We can deal with the entire device like that. We probably shouldn't. Let's move on to something that's a bit more cheerful, which is composting or anaerobic digestion. And we're starting to climb a little bit further back up the butterfly diagram now. So we're hoping to retain a bit more of that energy we've put into these products. We're hoping to keep those inside our economy. So composting is used for biodegradable materials. Fungal or bacterial decay breaks the material down. You get a mixture of outputs, but broadly what you get out is compost or anaerobic digestate, which is really quite highly nutritious. It's a bit thicker than soil, or biogas or methane-rich gases. The logistics, as they're done in the UK, are really quite similar to many of our recycling techniques. Actually, you have municipal collection from curbside in dedicated bins, which then splits between industrial composters and anaerobic digesters. But you also have an extra way, which is domestic composting. I don't know if any of you have a compost bin or a worm bin in your own homes. I do. It doesn't run very quickly. So I do what's called cold composting that runs about 30 C. Some domestic composters will run at 65 C. They aren't really comparable to industrial composters. They're not as quick, they're not as hot. And in terms of consumer choices, this is quite a difficult area to know what the right answer is. And there isn't a commonly used consumer label for biodegradability that has a firm meaning. And we're only just now starting to develop standards in this space. So there's an Australian standard that's quite well established for defining something as compostable, and that's about how much it breaks down. There's a French standard for biodegradability. And recently, the Belgian government has established two very useful standards, which are for industrial composting, that's the OK Compost at the top of the screen, and for home composting, which is the Home OK Compost at the bottom of the screen. So what these labels guarantee is that a product will disintegrate into pieces smaller than 2 centimeters across over 6 months. They won't leave dangerous contaminants in the compost. And in the industrial case, that's in a process running at 65. But in the domestic case, that's in a process running at 30 C, which is obviously, it's not going to be as effective an environment at degrading things. So if a material can meet that, it's very useful to know. But how does compost rack up in terms of the CO2 impact? Depends a lot on exactly how you compost things. So anaerobic digesters produce a methane-rich gas. This is typically used as fuel, normally on site, not much transportation going on. Sometimes it's the methane is extracted and that's injected into a local gas network. The side products like the municipal compost, that's typically sold on. Home compost in particular generally goes directly into domestic gardens, often into domestic food production. That's why in the Belgian standard there's such importance placed on the safety of the compost that you produce. There are a lot of benefits to compost. One of the things is that you don't end up with microplastics if you have successfully degrading materials. If they properly break down, the microplastics issue isn't a problem there. However, there is a pretty significant risk of methane all the way through this process. Anaerobic digesters exploit this. They make methane on purpose and they capture and use it, so they're pretty good. But in, say, domestic or badly managed municipal composting, where it's more open air and you don't have sufficient supply of oxygen, you can have really significant methane outputs, basically. And this leads to a really, really broad range of CO2 equivalent for this waste processing. So you might have as low as 0.2 kilos of CO2 equivalent. You might have as high as nearly 200 kilos of CO2 equivalent, and that will be driven by anaerobic decay in the presence of methane. So again, we're coming back to the same kind of themes of what's going into the waste stream and can we separate it out into these different parts. In terms of design considerations, you want to make sure you can split the compostable parts off. You want to know that those compostable parts are compostable. So, for example, paper is often absolutely fine. The inks on it often aren't. If they've got copper in them in particular, they'll slow down the composting process. So that's something you've got to be aware of when you're thinking about it. And one thing that is a little bit unintuitive is that anaerobic digesters shred most of what goes in as input, but the shredders aren't particularly good. They're sort of expecting banana peels and carrot peelings. They're not really expecting complicated polymeric structures, which is why quite a lot of compostable bin bags can't actually go into an anaerobic digester, because they tend to chew up the shredders. So while the Belgian standards are a pretty good starting point, there's quite a lot to think about. What it broadly comes down to is separability. Have you got something compostable? Can you get that separate to everything else so it can go into one of these industrial processes, be managed well, and you don't have plastics floating around, risking the quality of the compost, risking whether you get anaerobic stuff happening in pockets around them. The composting for our product really can only deal with the packaging. But that is if it's managed well, quite a good way of dealing with that packaging. So most of what we've looked at there has been quite heavily transformative. Landfill and energy recovery are very, very transformative, or you just don't do anything with the output. Composting, you get a whole new thing at the end. Let's now have a bit more of a look at recycling, which should hopefully, we're aiming to do a couple of things. We're aiming to avoid the extraction of more natural resources, and we're aiming to keep most of the embodied energy that we put in the first place and not have to keep rebuilding what we've already made. So let's have a look at some of the options around recycling. Recycling plastics. I'm afraid this is not a hugely cheerful slide. I don't know whether any of you have seen this recent report that the Centre for Climate Integrity have published. It's called The Fraud of Plastic Recycling. It, over about 60 pages, basically makes the case that the plastics industry is, at risk of legal action because of the degree of fraud that they've committed around plastics recycling. And it is true that as a field, as a waste stream, plastics recycling is not yet closed loop, and it's not widespread. So what I mean by closed loop is, if we go back to this diagram here, if something was closed loop, I could take one product, I could manufacture it as a part, and I could take it to a product manufacturer, I could take the service provider, I could take it to the user, I could run it through some kind of recycling process, I could get exactly what I started with out the top, and I could just keep going infinitely. So that's a nice closed loop. Plastics recycling in its current state is broadly open loop, by which I mean that you start off with quite a high grade plastic, something very high quality, perhaps something good enough to go into a medical device, perhaps simply something for the automotive industry, which similarly has very high quality standards. You run it through its use case, you recycle it, and then over the course of the recycling process, either because the waste stream is very mixed, so the output product is very mixed, or because the recycling process itself doesn't retain quality, you get something out the other end that really can't go back into the automotive industry, really can't go back into something medical grade. So it makes something simpler, something cheaper, something where the quality standards are a little bit broader. And then that process repeats and repeats and repeats until eventually you have a plastic you can't really do anything with. For mechanical recycling, that number's about 3 loops. So that's what I mean about not closed loop. We're not retaining quite as much of this energy, quite as much of this quality as we'd like to. We're also, bluntly, not recycling as much as we could. Across Europe, we get about 12% of our plastic waste makes it into the recycling route. The global high was 14% in 2019. So a lot of that's a logistics question. Some of it's a design question. In terms of ways to recycle plastic, that is looking a bit more hopeful. Mechanical recycling is quite well established, but we also have quite a few methods of advanced or chemical recycling that are now starting to make it up to industrial scale. So mechanical recycling, this is very well established. So for example, for PET, the EU actually has historically allowed recycled PET to be food contacting plastic. It hasn't really allowed that for any other types of recycled plastic. So that's an indicator of how well controlled this process is. The broad outline is you have ideally a dedicated waste stream, and in some cases, scrap from manufacturing sites, for example, you do get that. So you get just one type of plastic in your waste stream. Mostly for municipal waste, you have a mixed waste stream that is then collected and then sorted. So you're already starting to lose things. You're already starting to gain contamination. That's washed, that's shredded, that's melted and re-extruded. That's a very well-established route for PET and polypropylene. There is a recommend recycling scheme in the UK that's starting to do something similar for PVC. That's specifically clear PVC. I believe there are some routes for white PVC as well. On some later slides, we'll talk about the drop in quality in a bit more detail, but there is a distinct drop in quality through this recycling process. And that's because you have things that have been added. You have additives, you have impurities, you have colorants. If you end up with a lot of blue or green or just a mixture of colors coming into your input, your final product is probably going to have to be either gray or you're going to have to dye it black. And the fact that you can't make your plastic whatever color you want it's a drop in quality. It leads to a drop in price. And the fact that you've processed it also starts shortening the polymer chains just a little bit. There's just a bit of damage. The molecular weight distribution shifts shorter, and you end up with weaker, lower quality, slightly more variable plastics as a result. It is worth saying on the food contacting plastics front, recycled PET is not going to be the only one forever. Recently, the EU have made a legal route for trialling new versions with lots of data collection to see what's going on. But hopefully we're going to have more options for food contacting plastics quite soon in terms of recycling routes that get us there. Chemical recycling or advanced recycling is a really broad topic. So you've got things like glycolysis, you've got methanolysis, you've got pyrolysis, you've got steam hydrolysis. And what all of these things are aiming to do is use chemistry to get back to a pure product. So with dissolution, what you do is you dissolve your feedstock, having sorted it very carefully, having cleaned it very carefully, and you aim to pull into solution just the polymer you're interested in, and you then re-extract that through a few more chemical steps. So that approach requires a very clean input, and it focuses on a single polymer type, but you do get a single polymer type back out the other end. Some methods, specifically pyrolysis and steam hydrolysis, these are more generalist. So Mura actually fairly recently opened a site in the UK. They've got another one in Korea, another one in Germany, another one in the States. And what they have is a steam hydrolysis based facility, which should be able to take a mixed input. They claim to be able to take in pretty much any kind of unrecyclable plastic. And what they do with that is they then use hydrolysis and high pressure to break that apart into a hydrocarbon mixture of fairly short chain molecules. The output is very similar to oil. These generalist methods don't give you a polymer out the other end. They give you a mixture that's in behavior and appearance, it's really quite like crude oil. What you could do with that is fractionate it, filter it, use it as feedstock for making more plastics, and those would be equivalent to virgin plastics. What currently happens to them mostly is they get used as fuel in place of oil. So they still get fractionated, but instead of making our fuel from crude oil we've extracted from the ground, we make it from plastics we've collected from our waste. These technologies are pretty hopeful. They're not yet mature. They do get us around some of the quality questions, but we haven't quite reached the industrial scale cost savings or the really big logistics change that it would be nice to reach here. So just to dig into that question of quality a little bit more. So if you look on the lower table, you can compare some of the prices between virgin or brand new plastics compared to the cost for a mechanically recycled version, compared to the cost for a chemically recycled version. So for PET and polyprop in particular, you can see that you're losing nearly half the value of the product per kilo if it's been mechanically recycled. So in terms of the quality of it, it gives you an indication of the drop-off. That said, the top table should show you that mechanically recycling these polymers is worthwhile from a carbon saving point of view. Mechanically recycled polymers do have much less embodied carbon per kilo than the virgin material version does. The chemically recycled side of things, it's a bit more mixed. You can see from the two tables there that the price of chemically recycled stuff is generally higher. In some cases, it's even higher than the virgin material, than stuff made new. A lot of that is going to be to do with the fact that these are very small scale processes, and they don't have the cost saving effects of scale or having been industrially scaled up just yet. However, that said, some of that difference in cost is because the chemical recycling routes produce much better quality plastics. So even though the carbon savings, for example, for polypropylene aren't as good, you can see from the price difference that we're actually retaining a lot more quality there. So for plastics, I'd like to say there's a hopeful note in the air. We're not there yet. We've got big gaps in our logistics chains. We've got big gaps in our legal frameworks. And at the moment, given that we don't charge anybody negative externalities for producing CO2, economically, recycled plastics don't hold up very well against new. But I do think the chemical recycling routes are very hopeful. Moving on to the other materials that we're finding inside our example device, specifically metals and glasses, we've had these a lot longer and we've got much better recycling routes established for them. Again, in terms of the logistics, we have the same kind of things happening. The waste is collected, it's sorted to retrieve the valuable materials. In this case, steel and glass are valuable materials. They are retrieved. These are further sorted and washed. Some waste streams are pre-sorted. So, for example, demolition waste steel tends to be sorted almost on site, and it's sold on to scrap merchants who want to come and buy it. So instead of a municipal authority having to pay to do some of this sorting, a lot of this sorting happens because these things are valuable enough that people want to buy and trade them. In the case of glass, you have a lot of sorting because the colour is very important. But you also have very effective recycling. So Austria, Belgium, Germany are all recycling more than 80% of their glass waste. I'm afraid the data for the UK isn't particularly available. I think the latest thing gov.uk could offer me was 2018, which was a bit out of date. But glass recycling is so well established that you typically have recycled glass in most glass production anyway. So the examples I've given actually start from 10% recycled glass in your input versus fresh sand. And you can see you can drop just over 30 grams of, 300 grams of CO2 equivalent per kilo if you go up to 50% recycled glass. And you don't have to stop at 50%, you can keep going up. There is, again, always the question of a slight loss of quality. You do lose purity, and there are additives in some forms of glass that make it inappropriate to recycle into particular other forms of glass. That said, if you can keep your waste stream sorted by type of glass, you can keep moving that stuff sort of through our circular economy for a really long time. Steel is mostly recycled by being used as input into electric arc reduction furnaces. So electric arc reduction is sort of the modern version of steel making. Historically, we've relied very heavily on blast oxygen furnaces, and the majority of the world still does. These use coke or coal and directly produce a lot of CO2. But if we can shift to electric arc furnaces, any of you with a understanding of the steel making process will be thinking about electricity usage at this point, and you're definitely right too. But if we can make that shift, you can see the savings available are really quite dramatic. It's 2.23 kilos of CO2 equivalent to make a kilo of new steel in a blast oxygen furnace. If you convert a kilo of scrap steel into a kilo of recycled new steel in an electric arc furnace, it's less than a kilo of CO2. So in all these cases, we are seeing a bit of a drop in quality, but particularly for metals and glasses, we really can keep these materials inside our economy for a very long time. And it's worth making sure that the products we design are separable and it's easy for consumers to get things back into that system. So when we're thinking about designing, I know I'm banging on this drum quite hard, but separability really is key. And the other thing that's useful to know is traceability. The reason we care about this is we care about what's happened to the materials, because the quality of the input into our recycling processes defines the quality of the output. A particular example here would be limonene, which it's a lemon scented flavouring. It's common in a lot of cleaning products. It's common in a surprising number of beauty products as well. And it dissolves quite neatly into most plastics. It's a fairly small molecule. It very happily wiggles in amongst other polymers. It's also extraordinarily easy for humans to taste or smell. It's one of the compounds that we can detect most easily, sort of down in the tens or ones of parts per million. We can pick it out very easily, which means that if you have a beauty product in a plastic container that contains limonene and you then recycle your plastic container into something food contacting, there will be limonene in the recycled container, and that will make its way into the food in incredibly low amounts, nothing like enough to cause any kind of harm, but it will be enough that whoever eats that food will taste lemons. So if you know whether the container's had limonene in it or not, you know not to put it into a recycling stream that's going into food contacting. It could very well go back into another beauty product or something else, but knowing what things have been in contact with can actually inform a more effective recycling route. And the EU have begun a plan, so the Digital Product Passport plan, the idea of which is to have this kind of traceability for a very wide range of products. They've allowed some exceptions for things like feed supplies and pharmaceutical products, but what they are suggesting is that there is some kind of digitally accessible record of all the events between raw materials and finished product. And what this should allow you to do is very quickly understand something's product history and know how contaminated it is or isn't, which then tells you how you can or can't recycle it. All of this really brings us back to the same questions for design, though, which is, can we avoid contaminants? Can we avoid colorants where possible? Could we avoid fluidizers, or could we at least track them? And when we know we've got very different materials, can we find a way to easily separate them? So what that image is hopefully conveying is that inside this device, there is some kind of glass vial holding the drug. We can recycle that as glass. We've also got the plastic casing. We have plausible routes for beginning to recycle that. We've got the cardboard packaging. We can recycle that. Cardboard doesn't recycle brilliantly. It can't go around the loop many times. There's a real quality drop off, but we can recycle it. Or we could compost it, as we've discussed. But all of those things need separate routes. So we're back to this idea of being able to separate stuff out and having the smallest possible disposable chunk, basically. Recycling can handle most of this device. It probably won't be able to handle the needle because we've had that hazardous contact with a patient, but were it some other piece of steel, spring perhaps in a toy, that could easily be recycled. But the last route I'd like to talk about is actually not a disposal route at all. It's reuse. The idea of reuse is the product hasn't actually come to the end of its natural life. The consumer might be done with it, but it could be used again for the same purpose. We might need some intermediate steps, but we don't have to throw away or even reprocess this device. It can continue being what it already is. So there's a range of approaches here. I don't know how many of you are familiar with zero waste shopping. So the idea is that consumers bring their own containers and they just weigh out as much of whatever they want to buy, tea leaves, mostly dried things, chickpeas, lentils, dried mushrooms, into their own containers. They provide and they manage their own containers and they pay by weight. So the consumers there are responsible for bringing a suitable receptacle and maintaining it. There's also the German Pfand system. So when you buy a bottle of beer or water or fruit juice in the German supermarket, you pay a cash deposit on it. And when you've emptied that bottle and cleaned it, you bring it back to exactly the same supermarket, or indeed any supermarket. So you take it with you on your next supermarket shop. You return those, you get credit, which is you getting your cash deposit back, and the bottles return to the original owners, the original manufacturers, who sterilize, refill, and sell them again with fresh contents. Milk bottles, glass milk bottles, as delivered by milkmen in the UK, even easier. Filled bottles are delivered to the doorstep either late at night or early in the morning, and at the same time, the empty ones are collected. So from the point of view of the user, the end user, their use case is they walk to their door, put down an empty milk bottle and pick up a full one. It's a really, really neat piece of logistics. But I do want to point out a fourth example here, which might not obviously look like reuse initially, and that's infusion pumps in hospitals. So if you're giving a dose to a patient over perhaps a longer period of time, you might have an infusion pump. You could do that with smaller doses with single-use syringes and throw them away every time. We don't. We've decided that it's better to use infusion pumps, which have disposable parts that go in contact with the patient, and non-disposable reusable parts, which are wiped down, they're trackable, and the healthcare professionals in the hospital manage those transfers between patients. So that includes wiping down, sterilising the infusion pumps between uses. It includes removing and disposing of those contaminated disposable parts. And it includes keeping a track of what's been used when in order to know whether you need to service anything. Generally, the CO2 equivalent impact of this approach is beneficial. Every now and then, when the logistics of transport or reprocessing get too difficult, you'll find something where the disposable option is better, but it's pretty rare. Broadly, you get a reduction in embodied carbon because you're amortizing that embodied carbon over multiple uses. And the more energy you've put into something, the more energy intensive something is to make, the more savings are available. What you eventually end up running up against is that your in-use emissions become quite significant. But if you consider a glass bottle, if you reuse it 10 or more times, you're looking at a reduction in the CO2 equivalent per use of about 50%. And with an HDPE bottle, it's as high as 65%. That'll be because it's lighter, it's easier to transport. When you're designing for this, it's a bit of a different approach to the disposable approach. It's going to be more expensive, for example, and you're going to need to use hardier materials. But it's not a new approach. We have a lot of products that already do this. We know how to design for this. You do need to put a bit of thought into the logistics. You do need a plan for collection, you need a plan for processing. And your products need to be able to stand up to that. And you might need some infrastructure for quality control. So you might need regular servicing for your infusion pumps, for example. You might need something on your milk bottle filling line that just checks for overly damaged bottles and removes them before filling. The really important thing here is if you dispose of a disposable product, not ideal, you're losing embodied carbon, but compared to disposing of something that's designed for reuse that could have had another 10, 20, 200 uses, losing a reusable product is worse. So it does need to be really easy for the consumer to get this right for this to work. If we're thinking about our auto-injector, it's actually already a reusable version. You could deliver this drug, which is taken, a daily injection, a couple of daily injections. Those could be individual syringes every time. They're not, because for patient comfort and patient control, having an auto-injector is better. So we've already made it a bit reusable. If you were going to reuse it between users, you'd need quite a lot of infrastructure and you'd need some redesign. You'd need to be able to check that it was still safe to use. You'd want sterilization and refilling processes. And things like the drug cartridge and the needle are still going to be hazardous and are probably going to need to be removed between users and fresh ones put in. But it is already a reusable device. The one thing reuse can't really help us out with here is the cardboard packaging. We could make a reusable version of the packaging, but it's not going to do what we want, really. But the biggest part of this device, the greatest lump of embodied carbon, as it were, is the device itself, and we can make that reusable. Okay, how are we doing for time? Right, I will sum up there. So in summary, we've had a look at some of the things you can do once a product has reached the end of its life with a particular user. We've talked about how you can landfill it, which isn't great, but for some plastics might be the best we can do. We've talked about incineration, which is a safe option for hazardous waste, but broadly isn't something we should aim for. We've talked about some of the pitfalls around composting, and we've looked at some of the logistics you need for a good recycling system and the logistics you need for a good reuse system. I hope that that's been useful. I will try and end on a hopeful note, because this isn't a very cheerful topic to look at, I find. So I think I'll end by pointing out that we are making progress here. We do have chemical recycling routes that are starting to look plausible. Recycling rates are heading upwards slowly but surely. And in terms of our energy infrastructure, we are steadily greening the grid across Europe. It's slow, but we'll get there. And we have legal backing now behind good sustainability reporting standards across the EU. And Joe Biden's Inflation Reduction Act has been pushing green energy very hard on the US grid. which is all to say it is not all doom and gloom. And all that leads me to say is thank you very much for listening. I've put my contact details up on the screen if anyone does want to get in touch later. I think maybe Oliver, we could share those afterwards. But thank you very much for sharing so much of your Monday evenings with me. And does anyone have any questions? Okay.
Got a question in the chat. I'm not sure whether you can see that.
Yes, I can have a look at that. So I've got, does the use of recycled materials inhibit traceability in components compared to new materials, especially as it is very important in aerospace parts? So to an extent, it can and it will, because if you've got a recycling process, you're introducing new things. So you've got a sort of a set of unknowns coming in. There are sort of technical processing ways you can get around that. To my knowledge, I'm not aware of anyone in the aerospace or medical industries who are starting to use recycled products. The stress there always seems to be, at least for medical, on things being recyclable. So moving forward, hoping things go into the recycled ecosystem. But you can do a certain amount of quality checks, basically as your plastic feedstock is coming through. You can do quite a lot of chemical analysis to understand what you've got in there. And those techniques can be quite thorough. You really can pick out what's going on. So for example, FTIR and NMR let you pick up contaminants quite effectively, so does EDX. However, all of this is an extra cost. It's an extra load on whoever's selling your product to you. So in terms of making the cost benefit work, I think we're unlikely to see recycled aerospace parts anytime soon. But technologically, recycled material doesn't have to inhibit traceability, particularly if we have some kind of digital tracking system, such as the digital product passport. I hope that answered your question. Okay. Gerard's got a good point. The key, it seems, is that unless the human is motivated financially, recycling is slow to catch on. Yes, very much so. Obviously, I can't speak for all of you, but I certainly am a scientist by training and inclination. I really like having numbers in front of me and just sort of following things through rationally. So when you say to someone whose mind works like mine, the planet is heating up, we need to stop extracting resources, here is a way of stopping doing that, I'm very happy to get on board with it. And then you look at the way people behave in a much broader sense, and there's all sorts of other constraints on people's time, constraints in terms of money, constraints in terms of access. And broadly, what pretty much every human, and I include myself in this, ends up doing is the cheapest thing. I think it's up to probably a sociologist and an economist to work out what the best way of using money to leverage those behaviors is. Lots of people talk about having carbon credits. Personally, I think I find the idea of having carbon credits that you can trade really quite frightening, because I've seen what the free market's done with a lot of other things. I work adjacent to the medical industry. Some of the things the free market's done are really quite frightening. But the idea of having dedicated carbon credits that you can't trade, perhaps there's some worth in that. There's certainly some worth, I think, in a polluter pays approach. So that's the one that the EU are currently taking. America, not so much. The UK, to an extent, in that we still have some EU law on the books. And the idea there is if you introduce a product into the market, you are responsible for removing it again. So the best example of that is probably battery, specifically lithium battery recycling in the EU. You'll notice that lots of places have battery recycling sites now. That's because the people selling those batteries into the market are under a legal obligation to provide a route for you to take them back. And because they're under a legal obligation, they now have to spend the money or they will be fined. And therefore, there is now a route for battery recycling, which means we're retaining more lithium within Europe. So yes, you're exactly right. Financial incentive is our main lever here. Okay, I think we've got a few more. What about labels on products, e.g. shampoo bottles? How do they affect recyclability? They often seem very difficult to remove and are often a different material and use different adhesives. Are there any best practices for them? Well, there's two approaches you can take there. I'll start with the one where we dispose the item. And basically, yeah, taking the label off is your best bet. The label itself is going to be a real mixture of things, probably 2 or 3 like layers of polymers stuck together, then your adhesive, and then also everything that's been printed on, so quite a few different inks. That's not really recyclable at the moment. It would have to go into chemical recycling. It's probably going to end up in landfill. Excuse me. The bottle itself, that's likely to be a bit more recyclable. It should have its polymer group mark on it, which should help you with that. But I'm going to suggest a second way, which is if it is appropriate for you, wherever you're at, if you can refill that shampoo bottle and use it again, you've saved an entire shampoo bottle's worth of plastic going into the system. So if you do have access to a refill option, there are a few sort of cosmetic shops that do this generally. There are also quite a few zero waste shops that will have a shampoo that they sell. It's not the best answer for everybody, but I do think it's always worth asking the question, do you have to throw it away? Is there a second way? Okay. Are you aware of any new regulations being introduced that may dictate the design or choice of device used, for example, by the FDA? So, in terms of regulations that dictate design, I think the producer pays principle coming into the EU is going to dictate it to an extent. People are going to want easy ways of collecting or separating things. One of the things companies are likely to look for there is it being easy to break their product into something they can sell to someone else. So it being easy, for example, to extract the steel because that's valuable and easy to sell on. In terms of medical devices, we're still very much operating under a patient safety first principle. That's not going to change. It's not going to change anytime soon. That is the driving aim. There's a general shift towards consumer perception of sustainability. That's not the same as legislation, because often what consumers want to see is words like biodegradable, and as we've discussed, if those go into landfill, those can be really quite dangerous. One thing that is coming in soon is the Corporate Sustainability Reporting Directive. That's currently coming into force in stages. So April 2024 is the next reporting deadline, and the larger companies are having to report first, and then the smaller companies will be last. What they have to report is the carbon emissions and environmental impact of their entire supply chain. So something that we're starting to see in our own work is clients want to understand what our Springboard's ESG policies are. What are we doing about our carbon footprint? What plans do we have to reduce it? How big is it? They'll be asking that of all of their clients. That, coupled with the fact that information is going to be publicly accessible in some format, that's part of the law, should be pushing people towards lower carbon options. It should be. That said, it's just a reporting law. There's nothing within it to try and encourage people to pick a lower carbon option. They're just being asked to make their numbers public. Okay. Promising startups or technologies around aerospace sustainability, which offer the most viability for industry-wide adoption. That is a little bit outside my wheelhouse, I'm afraid. Aerospace is not something I'm hugely familiar with. I certainly don't know of anybody using recycled parts within the aerospace industry. There are approaches to use of carbon fiber that might be relevant here, which are using sustainably sourced sources of carbon. That's probably worth you looking into if you're interested, but I'm afraid that's all I really know in that space. Yeah, that's a really fascinating question. If anyone does know, I'm also curious to know more. Okay, I think maybe one more question. Is that right for timing? Cool.
Yeah, absolutely.
Lovely. Can we not just limit the materials we use so we can recycle the few of them well? I want to recycle, but many of plastics can't be recycled or don't say they can, so there's still some confusion. I'm a material scientist. I think the fact that we have all these materials is very, very beautiful, but equally, had about 6 different plastics, and plastic 1 was green and plastic 2 was red, and so on and so on. It would just be very, very, very straightforward. I think the answer is probably, as a top-down thing, we're going to really struggle to impose it. From an engineering point of view, For all I joke that my engineering colleagues will only ever use steel 316 and PEEK, and honestly, the days where they use something else, I get very happy. We have a wide range of materials because we have a really wide range of use cases. And one of the things that you start running up against when you start trying to narrow your material choices down is you end up making things heavier or larger, and now your transportation costs start going up, particularly anything going into air freight. You make it bulkier. You're starting to add serious amounts of carbon just through having to transport it. That said, in terms of your own design choices, aiming for monomaterials is generally a good idea for recyclability. And in terms of sort of your choices as an individual human, you can probably try and avoid some of the less recyclable stuff on an individual level. This is not a problem that will be solved by individual action, but that is an individual action that will help solve the problem. I've got one more question if we've still got time, Oliver.
Yeah,
okay.
We do.
Cool. The solution for better recycling seems to be an organisational one. Why isn't this a UN issue to promote best practice? Well, I don't. So the UN has a series of sustainable development goals, and they do include aiming for low environmental impact. That's a bit broad. It's not as specific as recycling. And there have been some global efforts. So the sort of 1 through 7 chasing arrow symbols you see on your plastics, those are international. But yeah, it is a really thorny problem that stuff moves across borders in the way that it does. I think it was about 6 years, maybe 7 years ago now, that China closed its borders to European plastic recycling, because what was happening is it was going into open cast landfills or being burnt in China, and they didn't fancy dealing with our rubbish for us anymore. And frankly, that's a reasonable position to take. So we don't really have an international solution yet. I hope we will find one, but you're right that we need one. Oh no, another question has arrived, and that one's quite an interesting one. What hazardous or sensitive materials in military products provide recycling challenges? How can these items and waste streams be handled safely and properly? Oh, I can't comment on military. It's not an area I work in. If anybody does work in military and is happy to talk about it in a public Teams chat, please do join in. But those are the kind of products that you quite often end up incinerating, at least from a medical point of view. When we have sensitive stuff, it's either sensitive because it's biologically dangerous, or could be. Human blood products, for example, are biologically dangerous because they could carry pathogens. We don't know that they do, but they could, so we treat them like they're dangerous. Or the materials are basically things that belong to people. They're genetic material or their information, and they therefore need destroying quite thoroughly. The current approach is to incinerate. That is the general approach there. Whether that's the best one, the one we should keep using moving forward, perhaps we can find a better answer. But for now, stuff just tends to get burnt. Cool. I think that's all the questions. Thank you for everybody who said it was an interesting talk.